Hello everyone, welcome back to our probability statistics lecture series. Yes, in the first few lectures we discussed about the discrete random variables. So in today's discussion we'll consider the continuous random variable, right? So let us see the things. So in the real world scenario, it is not always so neatly categorized, right? So consider a scenarios where outcomes can take on any values within a range, countably, uncountably many values, right? So it is not a counting. You cannot even count it. So this kind of situation introduced the concept of random variable. Whereas in case of a discrete random variable, we count it, right? That number of, so the cases were finite or countably infinite set. Therefore, what is a continuous random variable? Unlike discrete random variable, continuous random variable can take uncountably many values over a continuous range, right? It can take uncountably many values. That is, they are possible values from an form an interval rather than a countable set, right? It will form an interval. Continuous random variable typically modeled quantities that can be measured rather than counted. So we have to measure them, like the various timings. What kind of time? Maybe the service time, installation time, download time, failure time. This kind of situation. We have to involve the continuous random variable and we have to measure the time. Again, sometime we have to do the physical measurement, right? Physical measurement. What kind of? Sometimes weights, height, distance, velocity, temperature, connection speed, this kind of measurement. So in all this scenario will involve the continuous random variable. Now, since the continuous random variable takes values over a continuous range, so their probabilities are described using a probability density function. So in this case, probability mass function will not work. That probability at a particular value, mass function is what? It was for discrete type random variable, right? So probability at a particular value we have to calculate, and then in this case, mass function will give the probability of all kind of particular values, where random variable takes the values. So in case of a continuous random variable, that probability mass function will not work. In this case, we have to consider the probability density function. And what is density function? The probability density function is this one. So let x be a continuous random variable. Then the probability density function of x is a function f x such that for any two number a and b with a is less or equal to b, probability of a less than or equal to x less or equal to b is equal to integration between a to b fx dx, right? So this function fx is called the probability density function. So what it gives? It gives the probability between two numbers a and b of the random variable x, right? So it is the integration between a to b fx dx. Now we all know the integration meaning is what? Where we'll see that this fx function is always a non-negative function. So its value is always greater than or equal to 0, any functional value. Right? Now we all know that what this integration means. In this case, involving this probability density function, it is giving the probability between the value a and b. And what it geometrically means, we all know. So if we have the x-axis and y-axis, and suppose your fx curve is something like that, your fx curve, right? Then this integration between a to b fx dx is what? So this is the curve fx, right? This is the curve fx. Integration a to b fx dx gives the area between the interval a and b under the curve fx, right? So this integration gives you, suppose this is the a value and this is the b value. if this is A, so within this interval between A and B and the area under the curve. So this area, right? So therefore, we can say that the probability that X takes on a value in the interval AB is the area above this interval and under the graph of density function fx, like this. So this is the curve fx and this is between A and B. So this area gives you the probability between, this area is actually the probability between the number A and B. I hope it is clear. Sometimes this fx function is referred as the density curve. So this is a curve, right? So the graph of fx, sometimes we call it as density curve. Now we will see some properties of this density function. The similar properties we have seen in case of our probability mass function as well. We have seen na probability mass function was a non-negative, like it said greater than or equal to 0, and the probability sum was 1. Same thing will happen in this case as well. So what is the properties of probability density function? So the non-negativity property, as I mentioned earlier as well, the probability density function is always a non-negative. So if x is always greater than or equal to 0 for all x between any real number, for all real numbers, and the total probability, that is that, like that means the measurement from minus infinity to the plus infinity, right? The total in probability across all probable possible values of x must sum to 1, right? That means the probability of the whole sample space, right? So it is minus infinity less than x less than infinity. It is minus infinity in infinity fx dx. That value should be 1. So the total probability must be 1. So this is again a very useful property. We can see it later on. We can use this property to see, to find some parameters. Very, very useful property. So these are the properties of probability density function. Now see, uh, let us see that probability at a single point using a PDF. Using a, like for this, at a single point x equal to some particular point, we will calculate the probability using the probability density function. Now we know the definition of it, we can apply it and we will get that value. So probability at a single point means what? P of, suppose at the point x is equal to a, we want to calculate the value. But this is nothing but we can apply our probability density function. For that we need 2 points, right? So here both the points can be the number a, right? So this is basically p of x equal to a. Now this has our, we have, according to the definition of probability density function, what is this? It is integration between a to a fx dx. But it is range is lower limit is a, upper limit is also a. In case of integration, we all know this value, this should be 0. So therefore this value is 0 and therefore probability at a single point is actually 0, right? So this implies that the probability mass function does not provide. Probability at a single point was what? It is the probability mass function, right? So what we have seen that the probability mass function does not provide any meaningful information in case of a continuous random. Whereas in discrete type random variable, it was have some significance, right? So therefore, we can make this statement, yes, as we discussed, that probability at a single point it is 0. Now, note that the probability of a continuous random variable falling without an interval AB remains the same regardless of whether the endpoints are included or excluded. What does it mean? That if you want to calculate the probability, whether the endpoints are included or not, it does not matter. So this is same as, it can be probability of, maybe the point A is discarded now. It is same as this. You can also think that it is probability of A can be included, but B may not be included. It is also same. It is also same as P of A less than X less than B. And why this is happening? Because probability at a particular point, it is zero, right? Why this is happening? This is because the probability of a continuous random variable taking any specific value is actually zero. Therefore, whether you are including the endpoint or not, it does not matter. All these cases, these values are same. The probability value is same within the range. I hope it is clear. Okay. Yes, that's what we discuss. Next. Now the relationship between the probability density function and the cumulative distribution function. Now this cumulative distribution function we have already learned in case of a while we were discussing the discrete type random variable in some of our previous lecture. So the cumulative distribution function CTF of a random variable x, it is defined by fx is equal to p of x less or equal to x, right? We all know. And according to the definition of PDF, this probability is actually minus infinity to x fx dx because it is up to the value x. But from where it starts, nothing is mentioned. That means you have to consider the all possibilities. So you consider minus infinity to x ft dt, right? So therefore, this is the that one-way relationship that if we have the probability density function, we can easily calculate the cumulative distribution function using this formula. Now, what will happen if your fx is given? That means your cumulative distribution function is given. You have to calculate the value of the PDF, the probability density function. That means your fx is given somewhere. You have to calculate the value of this small fx. Now we all know that it is actually the antiderivative, right? That capital Fx is an antiderivative of small fx. So how you can calculate? So this basically that f of small fx is actually, you have to do the derivative of capital Fx and you will get the value. It is actually the d dx of capital Fx and it is equal to f test of x because capital Fx was the antiderivative of small f, right? And therefore, if fx is differentiable, for that definitely you should have this capital Fx should be differentiable. Then the probability density function can be obtained by differentiating the cumulative distribution function. So fx is equal to f test of x, capital F test of x. So therefore, from this relationship, what we understand, if your this probability density, cumulative distribution function is given, you can calculate the probability density function just by doing the derivative. I hope it is clear. And not only that, because we know the fundamental theorem of calculus, that thing we have learned in our calculus course. So if we apply that, then we can calculate the probability that x takes in the interval AB, that means P of A less or equal to x less than B, it is basically A to B fx dx. But this capital Fx was what? It was the antiderivative of small fx, right? So this value is actually fb minus fa, that capital Fx value at the upper limit point minus the capital Fx value at the lower limit point. So fb minus fa by using fundamental theorem of calculus. So therefore, if you know the probability cumulative distribution function, you can also able to calculate the probability between an interval AB. I hope it is clear, right? So now we can summarize whatever we have learned for the case of continuous random variable and discrete random variable. So probability function is what? In case of a discrete random variable, it is probability mass function. So probability at a particular point. Whereas in this case, in case of continuous random variable, we have probability density function. So here no meaning at the particular point we have seen it is zero. So probability you have to calculate between the range, like in between two number, in between an interval. So how to compute the probability? In case of a discrete distribution, discrete random variable, probability of x belong to A, that means x is in the some event, it is the sum of all the probabilities where x takes the values. And in case of a continuous random variable, it is the integration in the interval where you are taking of the density function fx, right? Again, cumulative distribution function, how we have defined. So again, it is the it is the probability up to the value a. So it is sum of the probability up to the value a. Where in case of a continuous random variable, it is the integration up to the value a. So minus infinity to a fx dx, and the total probability, whereas in the previous cases in the discrete type random variable, the total sum should be 1, whereas in case of a continuous random variable, that in minus infinity to infinity, that fx dx should be 1. So either in this case, integration value from minus infinity to infinity, that value should be 1, right? So I hope we understood this comparison very easily if we understand the whole discrete random variable and continuous random variable, right? Now we'll solve few examples. So if a random variable x has the probability density function fx is equal to 2e to the power minus 2x if x greater than 0 and equal to 0 if x is less or equal to 0, then find the probability that it will take on a value between 1 to 3 and greater than 0.5. Now it is very easy. Once you have the probability density function, we can very easily calculate, right? So the probability between this one, so let us do this one between the point 1 and 3. How we can do? So the first part is P of 1 less or equal to x less or equal to 3. Suppose x is the random variable. It is given. It is the continuous random variable. So according to the definition of probability density function, it should be the integration between 1 to 3 fx dx. Right? But x value is greater than 0, then you will have this part. So we can directly write between 1 to 3 2e to the power minus 2x into dx. And if you calculate the integration, it is actually 2 into e to the power minus 2x by minus 2, right? And the integration is between 1 to 3. The 2 can be cancelled out, and if you just put the value, it is e to the power, so minus of e to the power minus 6 minus minus becomes plus e to the power minus 2. Right? So e to the power minus 2 minus e to the power minus 2. So approximately this value is, if you calculate it using calculator, it is 0.133. Very easy. Okay, the first part is done. Now let us see the second part. You have to find the probability that x takes the value greater than 0.5. What does it mean? That means P of x is greater than 0.5. So how we can calculate? That means it is from 0.5 to up to infinity. It can take the value, and then fx dx. Now again, x greater than 0, we have this value, so we can directly put. So 0.5 to infinity to e to the power minus 2x dx. And the same way we can calculate, and it is minus of e to the power minus 2x and between 0.5 to infinity. Now if you put the infinity, the first part, it will be 0 plus e to the power 0.5, so e to the power minus 1, right? And this value is again approximately 0.368. Easy? Okay, let us do few more example. This one we have already done. We may take a snap of it. We already did it. Look at this problem. Suppose a random variable x has the probability density function given as fx is equal to this value. Just a minute. So this is the fx is equal to this if x is lies between 0 to 1 by 3 and otherwise it is 0. So we have to calculate this probability. Again, we can easily do that. We know the formula. If your probability density function is given, we can easily find out. So the first part is P of 0.1 less or equal to x less than 0.2. So what is this value? It is integration between 0.1 to 0.2 fx dx. And see, this 0.1 and 0.2 is lies within this interval, so we no need to worry at all. So 0.1 to 0.2 and 3 dx. So 3 can be taken out into x. If you do the integration, it is 0.1 to 0.2. So it is 3 into, if we do 0.2 minus 0.1, so 0.1, therefore it is 0.3 is the answer. What about the next one? Probability of 0.1 less or equal to x less than 1. So again, according to the definition, 0.1 to 1 fx dx, but after 1 by 3 the value is 0, right? So we can consider only up to 0.1 to 1 by 3, because from 1 by 3 to 1 this fx value is 0, this fx value is 0, so we will not consider this one into fx dx. And 0.1 to 1 by 3 the value of fx is 3, so 3 dx. So it is, again if you do the calculation, the 3 into this, it is 0.1 to 1 by 3, right? And therefore it is 3 into 1 by 3 minus 0.1. And if you just calculate, you will be getting this value is 0.7. This problem is also done. So what we understand, if we have the probability density function, we can easily calculate the probability of the random variable takes the value within some interval. Okay, yes, we have done this one. Now let us see this example. This kind of example we have done for the case of a discrete type random variable also. That you have to find the parameter, right? So let x is a random variable with probability density function given, which involves some parameter c, we have to calculate this value. So find the value of the c. So first we have to calculate this one. Now, which property we can apply so that we can get the value of c? Yes, the total sum should be 1. You can apply this formula and we can get the value of c. So the first one, to solve the first part, what we can do, because we know that the total probability sum is 1, so integration minus infinity to infinity fx dx should be 1. But minus infinity to infinity, fx is taking only the values between 0 to 1, some positive value, otherwise it is 0. So we can discard all the interval, because other places it is 0. It is between 0 to 1 fx dx, but in between 0 to 1 fx dx value is what? Cx square into dx. This should be equal to 1, which implies what? C into x square dx integration is what? X cube by 3. Between 0 to 1, it is 1. And therefore C into 1 minus 0. So therefore C into 1 by 3 minus 0 is equal to 1. And this will imply that C value is equal to 3. Easily we calculate the value of C. Okay. What is the next question? Find the cumulative distribution function CDF of x. How we can do that? The cumulative distribution function. See that cumulative distribution function, it is a piecewise defined function, right? So you can take, if your a value is up to 0, what is that value? If it is between 0 to 1, what is this value? And if it is above 1, what is this value? So in this way, but in this 3 interval we have to calculate. How we can do? Let us do that. So for the part B of this question, so if you have for a less than 0, if I have a less than 0, then in that case what is fa? Fa is what? Integration minus infinity to a fx dx, right? But this fx value, whenever a value is less than 0, fx value is 0. So this value is basically 0 then, right? Why? Because whenever a is less than 0, suppose a value is minus 1. So in this case, 0 to minus 1, fx value is 0, right? And therefore this value, fa value is also 0. Okay. Now if I have a is lies between the interval 0 to 1. In this case, what is the value of a? Okay, let us see. So fa is equal to minus infinity to a fx dx, right? And so minus infinity to a, if a is between 0 to 1, so it is okay, I should take minus infinity, but minus infinity to 0, all values was 0. So I can just simply take, it is between 0 to a, because minus infinity to 0, that value is anyway 0. So I can discard that part. So it is between 0 to a fx dx. Now what is the value of fx in this interval? It is 3x square, because it was cx square, but the c value is 3. Therefore, it is 3x square dx. And if you do the integration, it is x cubed by 3. So this integration value is x cubed between 0 to a. That means it is a cube, right? And the last part, for if I have a is greater than 1, if I have a value is this. In this case, what is fa? In this case, fa is equal to, again the same definition, minus infinity to a fx dx. But a value is greater than 1, so minus infinity to plus infinity we can take. Because above 1, it is okay, minus infinity to 1 fx dx we can take, because a value is greater than 1. After that 1 to a value, it is anyway 0. So minus infinity to 1 fx dx will take. And it is again basically 0 to 1 fx dx. And 0 to 1 fx dx, what is this value? 0 to 1 fx dx, 3x square dx. And if you do, it is x cube over 0 to 1, and this value is actually 1, right? And therefore the cumulative distribution function is what? CDF of x is what? Capital Fx is equal to that the piecewise defined function. It is 0 if you have x is less than 0. It is what? It is x cube if your x is lies between 0 and 1. And it is equal to 1 if your x is greater than 1. So this is the cumulative distribution function. So here in this example, the probability density function was given. You calculated the cumulative distribution function. Okay. The last question was what? Compute p of x is less than half. Now this one we can do it in a two-way, right? We can do that in a two-way. P of x is less than 1. One is directly using the probability density function, right? Method 1, that p of x is less than half. So directly we can do it using the probability density function. So it is between 0 to half we can take, because before 0 all the value of fx is 0. So it is this into 3x squared dx, because 0 to half the fx value is 3x squared. And if you calculate, it is x cube over 0 to half, and it is 1 by 8 if you calculate. And the next method is method 2, using the, because you have calculated the cumulative distribution function. So p of x is less than half. It is basically the definition of f of half, right? And what is the f of half? Because you have already calculated the distribution function is this. Now f of half, that means x value is lies between 0 to 1. So it is x cube. Therefore it is 1 by 2 whole cube, and its value is 1 by 8. In both the method, you get the answer is 1 by 8. Clear? Okay. Now one more example. Yes, that's what we calculated. Let us do the very, very interesting problem. The lifespan in month of a certain type of light bulb is a random variable with a probability density function given by this. Right? So lifespan of a certain type of in months of a certain type of light bulb in a random is a random variable with the probability density function is. So if x is less or equal to 5, then it is 0. If x is greater than 5, it is 5 by x squared. Now the question is, what is the probability that exactly 3 out of 6 such light bulbs in a chandelier will need to be replaced within the first 10 months of operation? So this chandelier means what? It is some group of bulb will be there, right? So sometime we called it as Zarbati. So people used to keep it in their ceiling, right? The chandelier is some group of light bulbs. So the question again, is the probability that, what is the probability that exactly 3 out of 6 such light bulb in a sand layer will need to be replaced within the first 10 months of operation. Assume that the lifespan of the light bulbs are independent. So this part, that 3 out of 6 such light bulb, that light span of the light bulbs are independent. So can you see that it is actually the binomial random variable, right? It is talking about that you have to get 3 out of 6, 3 trial you will have, your total 6 trial you will have, and you have to get the 3 success. And each of them, each trials are independent, right? And here success means what? Success means what? That we need to replace the light bulb within the first 10 months of operation, right? So this part, that we need to replace the within the first 10 month of operation, this probability we have to calculate first. So what we'll do, the first we'll calculate we'll find the probability that a single light bulb lasts less than 10 months. So that means that is the probability of success. If it is lasts less than 10 months, that is the probability of success, right? So let us do this solution of this. So the probability that, first let us calculate this probability. The probability that a light bulb lasts less than 10 months is P of x is less than 10. Now this one we can calculate using the probability density function of x, right? So we can easily calculate. It is the integration minus infinity to 10, right? And minus infinity to 10, what is this value? If x is less or equal to 5, it is 0. Otherwise, x is greater than 5. So this into fx dx. So this is basically 5 to 10, because less than 5, this value is 0 anyway. So it is 5 to 10 fx dx. But within 5 to 10, what is the fx value? It is 5 by x square into dx. And if you do the integration, it is minus of 5 by x, 5 to 10. And if you calculate, this value is actually 1 by 2. That means we got the probability of success. And rest of the problem is very easy. Now what is the probability that exactly 3 out of 6 such light bulb in a sand layer will need to be replaced with the probability of success is P, which is 1 by 2. So next part we can easily answer. Therefore, let x is the number of light bulb that need to be replaced. So let x be the number of light bulb that need to be replaced. And in this case, therefore, x is a binomial random variable. Binomial. N is what? N is equal to 6. And P is what? Probability of success. It is 1 by 2. Right? And what we have to find? We have to find P of x is equal to 3. So you have to get out of 6, you have to get 3 success, right? So P of x is equal to 3. Now what is this formula? It is 6c3 P to the power 1 by 2 to the power 3 into 1 minus P, which is again 1 by 2 to the power n minus k. So 6 minus 3, it is 3 again. And if you just simplify this, you will get this value is 5 by 16. Our job is done. So this problem is very, very important one, very interesting as well. So it is an involvement of continuous and discrete random variable both. Right? I hope you enjoyed. We'll meet in the next lecture with some new topic. Thank you very much.